So welcome everybody, this is Sivam back again with a new video on a video series of CSI and GRF, GATE, IIT, JAM as well as GSI. So in this video series, I am going to explain about planetary sciences. See, this is one of the very important topics, interesting topics in entire Earth science subject. But the thing is, this is ignored by every student. The thing is, see, this is not part of our course, right? But still, this is a part of our syllabus. Okay, this is there in GATE, NET, JAM, GSI, everywhere you get some questions. Yeah, I know it's very few questions are there, but still, even a single number is very important, right? So yeah, so in this video we are going to follow the book that is fundamental of planetary sciences, and using that book and using my own course in planetary science from University of California Irvine, I am going to explain this whole astronomy thing, planetary science thing to you in a very convenient way. So without wasting a time, let's start. Okay, so here we have syllabus of GATE, GSI, CSIR as well as JAM. So let's see first GATE. In GATE, according to latest syllabus of GATE 2020, the most important, you can say, topics of this planetary science are: first is basics of planetary system, solar system, gravitational field of Earth, geomagnetism, Kepler's law, Milankovitch cycle, and cosmic abundance of asteroids. So these are common for geology as well as geophysics student. For part B, the things are like paleomagnetism, geothermics, heat flow. These are important. Now these topics are either directly related to planetary science, and sometimes it is indirectly related also. Okay, so same syllabus is over here in GSI, but new things are like rotation of Earth, revolution of Earth, geoids, spheroids, topography, shape and rotation. These things are new, okay, except everything is same. In CSIR exam, the syllabus is very enormous. Okay, and the number of questions are also very large over here in a case of CSIR. So here we have again same syllabus like GSI, like GATE, but new things are over here. Here we have some topics like Earth's orbital parameters, space type concept, Milankovitch cycle and its effect on climate. So here we have relation of this planetary science with atmospheric science, with oceanography and all. Okay, now if you see the numerical, we have some numericals based on planetary sciences. Like the first one is based on Kepler's law. It is there in every exam except GSI. Okay. Third one is based on orbital velocities, orbital velocity, escape velocity. Okay, these things are common in each and every exams. IIT, JAM, GATE, and NET. So that's it. Now, if you see the most important topics for GATE, NET, and IIT, JAM, first thing is Kepler's law. Theoretical parts of Kepler's law is very important. Second one is Milankovitch cycle. Third one, it's a relation with atmosphere. Fourth, entire solar system is very important. Please mind it. It is very important. Solar system part. Okay. Now, why this is important? Why planetary science is important? Now, for the exam purpose, we know questions are few and very few students like simply solve this, okay, because they don't have knowledge now. So better please go through it, get the knowledge and solve it. Second, if you want to join institutes like ISRO, any space agency, then you have some idea about it, right? if you want to do research in this field. So for that, you need some idea. And I'm going to give that idea to you, okay, directly. So see, this video is a demo video. This video is a part of demo part. Okay, this is just a trailer. The entire movie is still remaining. Okay, so join Career Avenues. We'll discuss this entire planetary science in 30 hours. Okay, and in this 30 hours, I will give you 10 lectures of 3 hours each. It is going to be very interesting from the origin of the universe till now. What is there in the space science, this astronomy, okay, planetary science. So these things are there. Now let's start Big Bang, the origin of universe. So before that, I will follow this book as well as my ebooks from University of California, Irvine, as well as some data from ISRO websites. So that's it. Now let's discuss about Big Bang. Okay, now we have lots of theory regarding the origin of universe. But the most verified theory, the most you can say well developed theory, or the theory uh, which is used by everybody, that theory is Big Bang theory. So what is Big Bang and how it forms? What is there after Big Bang and before Big Bang? Let's see. So initially we have a tiny point universe. Actually, there is no universe at that point of time. The entire universe is in a tiny point. That, and the size of this point is less than the size of, you can say, atom. Okay, here it is infinitely hot, infinitely dense. The shape is nothing. Shape is zero. Okay, time is zero. Even time is not there. No time. Okay, there is no space, no vacant thing. That is space. Space is zero. Density is infinite. Entropy is infinite. Infinite. Density, this temperature is infinite. Now, due to certain force, we don't know what force is, like what that force is, but due to certain force, due to godly power, whatever you can say, okay, due to some force, it explodes. And the time of explosion, everything is start forming, everything start taking place in a right way. Okay, so initially it is like a supercharged black hole, you can say. It's infinitely tiny and it is highly charged, ready for explosion. Okay, so let's see next slide. Here we have similar to the supercharged black hole before explosion. After explosion, it forms energy, it forms matter, it forms space as well as time. Now, matter, anything that occupies space, yani matter form hua, then we have space also. Energy, energy is a, you can say, any thing which is required to do work, that is your energy. And time, everything forms from that point of time, from after Big Bang, you can say. Okay, now let's see next slide. So then we have two eras after Big Bang. The first era is called radiation era. Over there we have radiations, we have electromagnetic energies, electromagnetic waves, but there is no matter at all. So we have light at that point of time, but there is no matter, there is nothing to occupy space. Then we have a matter era. Just like geological time scale, we have eras, eons, right? We have two eons, we have eras, different eras, periods. Similarly, the whole Big Bang is divided into two major eras. The first one, radiation, and the second one is matter era. Now let's see radiation era. First one is radiation era. So in radiation era, there is a dominance of radiation. It doesn't matter at that point of time matter is there or not. See, matter is there, but still radiation is more. Okay, So at the last of this radiation era, you have some these things also, atoms are there, but majority is radiation. Okay, now in radiation era we have the first, see, we have the first epoch, that is Planck epoch. The whole radiation era is divided into different epochs: Planck epoch, grand unified epoch, then inflationary epoch, electroweak epoch, quark epoch, hadron epoch, lepton epoch, and nuclear epoch. So in this way, this is the earliest epoch, and this is the end of radiation era. And from here, matter era starts. Okay, so let's discuss about Planck epoch. So see, this is the Big Bang, and just after the Big Bang explosion, Planck epoch starts. At this point of time, the temperature of the universe is 10 to the power 40 Kelvin. Okay, this is 10 to the power 40 Kelvin. Okay, and this is the highest recorded temperature till now. So it's not a recorded, it's indirect technique through which we can generate these kinds of data. Okay, through indirect technique, I will tell you in detail in lecture number 6. Okay, how we come to know that 10 to the power 40 Kelvin is there at that point of time. We'll discuss this. It's a immediate time after Big Bang. Now at the Planck epoch, there is no force at all. There's nothing like gravity, strong nuclear force, weak nuclear force, electromagnetic force. Nothing is there. There is no force at all. We have certain radiation. That's it. That's it. And space is forming. Okay, time is forming. Then, so at this point of time, only energy is present. No matter existed. Energy in the form of radiation. Okay, energy is there, but in the form of radiation. There is no force. Now, the second one is grand unification. Unification means now everything is start combining. Why combining? How combining? Because of gravitational force. Now here we have gravity, effect of gravity. We know gravity is due to mass. That means now these radiation have some particles, and these particles have certain mass. And due to this mass, there is a unification, right? There is a unification. At this point of time, the temperature is now 10 to the power 36 Kelvin. Initially, it is 10 to the power 40. And it is only 10 to the power minus 43 seconds after Big Bang. Now see, minus 10 to the power 43 second, 10 to the power minus 43. See, this is very small time, right? It's a less than nanosecond, man. This is less than nanosecond. And think, so at this point of time, now we have a gravitational force. It's a kind of attractive force. Now due to this attractive force, we have unification. Okay, now moving to the next. This epoch is called inflationary epoch. Now, at this point of time, there is expansion with moving time. So here we have something at the size of say quarks, even less than quarks, and till the end of this epoch we have bigger objects. Okay, the space is of the size of bigger objects. Dhire space starts increasing. Space increase kar raha hai, right? Now temperature over here is 10 to the power 33 Kelvin, and the Big Bang, it's just after 10 to the power 36 seconds of Big Bang. So here we have expansion of universe, and still after the Big Bang itna time ho gaya, right? Right now it is 13.7 billion year after Big Bang. So still our universe is expanding. Okay, moving to the next. Here we have inflationary epoch, and in this epoch there is a formation of electrons, quarks, antiquarks. Now to form quarks and antiquarks we need very high temperature. Now think of it. Here we have 10 to the power 33 Kelvin, right? This is very hot, right? Very warm conditions. So at that temperature, atom can't exist. So atom is in the form of now electron, quarks, and antiquarks. And with time, these quarks combine to form proton and neutron. We will see there are different types of quark also, up quark, down quark. So we will see everything. Now here in electroweak epoch, we have now all the forces. So initially we have gravity, now we have a strong nuclear force which can now form nucleus of atom. We have electromagnetic force. We know that electrons revolves around a nucleus in a closed path, and since electron has charge on it, that means a charge is moving in a closed path, and whenever charge moves in a closed path, it produces electric field and magnetic field. So that's why we have electromagnetic force also, and there is a weak nuclear force also. Okay, so here temperature is very less, and now from 10 to the power 40 Kelvin, it's 10 to the power 20 Kelvin only. So now we have atoms, formation of atoms. We'll see how first proton and neutron forms, and once proton and neutron forms, then due to this strong nuclear force, they combine with each other, then electron revolves around it, and we have then first atoms like hydrogen and helium. We'll see it. So here we can see this is a quark epoch. That means here quarks are formed at a rapid rate. Here we have different types of quark, up quark, down quark, like this. We have electrons, we have a lot of subatomic particles. And after this, now due to merging of up two down quarks and one up quarks, two down and one up, it forms a neutron. And in proton we have two up quarks and one down quark. Now the temperature is very less, it is 10 to the power 10 Kelvin, and here at this temperature these quarks bind together to form neutron and proton. Now let's see here. After this we have a first atom. See, here we have two electrons revolving around the nucleus, having two proton, two neutron, and it's no doubt it's a helium atom, right? It's a helium atom. So here we have helium in lepton epoch, and finally in the nuclear epoch we get this nucleus, and here we have first atom, that is helium. Okay, now moving to the next. So here, from here we have now matter era. So radiation era ends in a nuclear epoch. Finally we have a matter era. So now let's see matter era. The first epoch of matter era is the atomic epoch. In atomic epoch we have atoms of hydrogen. Remember, initially we have helium, so that means helium form first, then atom forms. Okay, why helium form first? Because before formation of helium we have neutron and proton, and we know that in helium we have proton and neutron both, while in hydrogen we have only proton, there is no neutron at all, right? So after this epoch, after this nuclear epoch, in atomic epoch we have hydrogen finally. Okay, so remember hydrogen is formed later, after you can say 50,000 years of Big Bang. So this is the present time, this is the Big Bang, suppose it is over here. Now difference between the present and the Big Bang is 13.7 billion years, and this atomic epoch is after 50,000 years of Big Bang. So this is the zero time, and after 50,000 years hydrogen is formed, recombination takes place, and finally we have hydrogens. Still the temperature is 3000 Kelvin. 3000 Kelvin. Right now 3000 Kelvin is the temperature of our mantle. Okay, so now moving to the next, we have galactic epoch. So in this galactic epoch, finally there is a formation of nebula. Nebula is basically a cloud of dust and gas. Okay, which is you can say where star originates, where star forms. So this is called galactic epoch. Galactic bodies are formed somewhere 200 million years after the Big Bang. Okay, moving to the next, we have now stellar epoch. So now these nebula merged together due to gravitational force, and now they converted into stellar epochs. Now we have galaxies, the bigger bodies, very gigantic bodies of the universe, and it is formed after 3 billion years of Big Bang. So this is the last epoch of matter era, and we are right now in the stellar epoch. Still, some galaxies are formed and some are getting destroyed by supernovas, by you can say dead stars and all. So this is the thing. Now let's talk about solar system, our solar system. So our solar system is 4.6 billion year old. Initially, we have a nebula. Okay, so this is the nebular hypothesis, and this is the most important hypothesis regarding our solar system. So around 4.6 billion year ago, we have a nebula, a very big nebula, which is formed due to you can say death of a star. So whenever star like explodes due to deficiency of fuel, it forms clouds of dust and particles. And around 4.6 billion years ago, we have this nebula. Okay, it's a wispy cloud of gas and dust. Now, due to certain, you can say, gravitational force inside this nebula, there is a coalescence of entire gas and dust. And slowly, this cloud get converted into a bigger cloud. You can say bigger cloud, no, dense cloud. You can say, yeah, dense cloud. And due to this dense cloud, due to this gravitational force, slowly it get converted into a spherical shaped body. Now, since it has some angular momentum along its own axis, it starts rotating on its own orbit. Okay, now this, if you rotate any sphere with a very high speed, it bulge out at the equatorial region. So just like on our Earth rotates on its orbit in a you can say cruise path, right? Orbit per it moves like from west to east, and due to the high rotational speed, we have some equatorial bulge. The radius at equator is more than the radius at pole. So what happens is, due to this rotation along its axis, here we have certain bulge. Now think of it, it is very gigantic in nature. Now slowly, this whole sphere get converted into disk. Okay, disk. This is now disk. So here we have disk, and in the central part, we still have some spherical bodies, which is now sun. Okay. Now, as a result of flat spinning disk of dust and gas, there is a formation of rings around the central mass. So in central mass, we have still certain gigantic body, while on the outer limits, we have now rings. Now the whole disk get converted into rings. And in each ring, we have certain gaseous particle. We have certain dust. Now these dust and gas, rocky bodies, slowly, due to gravity, they merge together and form different belts. Okay, and these are either planetary belts, asteroid belts, Kuiper belt, Oort cloud belt. It get converted into comets like this, meteoroids like this. Okay, while in the central region, we have enough mass that you can say that merge together to form a star. And now, if you have enough mass, due to this enough mass in the core of that mass, we have enough pressure also, enough temperature also, and that enough temperature and pressure cause nuclear fusion to begin. So in this way, our sun was born. It globbed together, and the mass of that sun is actually 99.8% of the total mass of solar system. So in this way, we have our sun and different planets, and each planet again starts revolving around a central mass. We know that if you have a massive body in the center, so everything is rotates around it. I will discuss in different chapter in space-time curve thing. Okay, in relativity part, Einstein's law of relativity. Okay, so I will discuss later. So till now, this is the thing. This is how our solar system born. Okay, so this is the typical present time solar system. We have different figure also. So yeah, initially we have supernova explosion in the star. That supernova forms pyramidal dust. This primordial dust condense to form disk shape, and in the center we have protosun. That protosun converted into Purgente sun, and on the outer limits this disk get converted into different rings. In each rings there is accretion of planetesimals, and then differentiation took place in different planets to form different layers of the planets like mantle, crust, core, and finally we have Purgente solar system. So this is all about origin of solar system. We have completed origin as well as origin of universe, origin of solar system as well as origin of universe. Now let's talk about our solar system in detail. So our Milky Way galaxy is one of the 500 in the this cluster. So each galaxy combined together to form clusters. Okay, so in this cluster we have our Milky Way galaxy. This there are billions of galaxy in the entire solar system. We exactly don't know how much it is, but it is more than billion, I guess. Okay, so this is our Milky Way galaxy. It is a spiral shape, and here in this Orion, this is the Orion spur. Here we have certain group of stars. In that group of stars, sun is over here. So this is galaxy, Milky Way galaxy. In this Milky Way galaxy, in the center we have a black hole. Quasars are over here. While at the one of the arms, these are the arms of Milky Way galaxy, and in one of the arm we have our solar system. Okay, in Orion spur. So we are a part of Orion system. Okay, now see. Okay, till now we considered that only 15% of stars host planets. Yani, remaining 85% of stars are planetless. There is no planet around it. Only 15% of the stars have planet, and sun is one of that. Okay, so this is our sun somewhere here. Okay, now let's see our planets. So we have right now 8 planets. Yes, Pluto is not there in this list. So Pluto is a dwarf planet right now. I will discuss it later. So let's start with Mercury. Believe me, this is not on a scale. Okay, the actual size is different. So yeah, the first one is Mercury, then Venus, then Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So this is the sequence from the Sun. Okay, of the 8 planets. Now let's talk about first planet. First 4 planets are terrestrial planets, and the last 4 planets are Jovian planets. Now, what is the difference in between them? So, the first and foremost difference here in a Jovian planet, the size is very gigantic as compared to terrestrial. Second thing, in Jovian planet, since its distance is very far from the sun, they are icy, they are gaseous giants or icy giants. While here it is close to the sun, here it is rocky bodies. Okay, one more thing, if you compare, these Jovian planets have a lot of satellites around it. Means the number of moons around these Jovian planets is very high. While in the case of terrestrial, it is less. And even there is no moon in the case of Mercury and Venus. Okay, so this is the difference. Let's see in detail. So these are the terrestrial planets. Okay, now let's see the properties. So they all are made up of rocky materials. Their surface is solid. They don't have rings at all. They are relatively small. Very few moons are there. On Earth, we have one moon. Its name is Moon. And on Mars, we have 2 moons. And its name is Deimos and Phobos. And there is no moon at Mercury as well as Venus. Okay. So now let's discuss about Mercury first. So this is the smallest planet in the entire solar system. Its orbit, shortest orbit in the entire solar system, it took around 88 days to complete one revolution around the sun. See, here Mercury is passing in front of sun, and you can compare the size. Mercury is just like a small dot on the body of sun, you can say, right? It's very tiny, very, very tiny. And it is one of the smallest planet in the entire solar system right now. Okay. See, now this is close to the sun, but this is not hot. Okay, this is not the hottest planet. Hottest planet is Venus, and this is a very important concept. We'll see why. The reason is on Venus we have presence of greenhouse gases like CO2. CO2 is very high amount over there, and we have sulfuric acids over there. These are heat trapping gases. They increase the temperature of planets. So we'll discuss it. Let's see. Here we have Venus. Okay, the atmospheric carbon dioxide. Here we have atmosphere of carbon dioxide, and the amount of carbon dioxide on Venus is around 95%. 95%. It is very high, right? See, on Earth we have 0.03% of carbon dioxide, and this is quite enough to melt our poles, to melt our glaciers. Right now it is melting. No, the whole global warming thing is there on Earth. Only 0.03%. And see, here we have 95% of carbon dioxide. This is very, very dangerous. Okay, very, very dangerous. And here we have extensive lava flows. Due to this lava flows, we have continuous oozing out of volatile materials. These volatile materials can be water vapor, it can be different poisonous gases, sulfurous acids, sulfuric acids, boric acids, different gases like carbon monoxides and all. And these all are greenhouse gases, right? Greenhouse gases, this is. So it has ability to trap heat, and once the heat will trapped in a planet, it will increase the surface temperature of that planet, right? So it is a hell-like condition on a Venus. Okay, so this is one of the warmest, or you can say most hottest, or you can say hottest planet in the entire solar system. Now Earth. So Earth is at a perfect distance from the sun, neither too far, neither nor too cool. Okay, मतलब ज़्यादा दूर भी नहीं है और ज़्यादा close भी नहीं है, right? So neither too far, neither nor too close. So it is at a perfect distance from the sun, and this distance is called habitable zone, Goldie zone, or habitable zone, where water exists in a liquid state. Now, liquid state water is very, very important. On Earth, we have liquid state water, vapor state water, as well as solid state water in the ice, in the glaciers. Okay, so water system here helps to create environment to sustain life, and this is the only planet where we have life till now. This is our study. Okay, maybe it is there on any other planet, but according to our study till now, we have life on the Earth only. Now Mars. So it is considered that around 3.7 billion years ago, there is a water on surface of Mars, and maybe there is a possibility that there is a life over there. But right now, things are getting changed. Right now, the whole Mars is barren. It is a red planet, right? Now, why it happens? Why all of a sudden life destroyed? Where is water now? So it's all because of its weak magnetic field. The thing is, right now the magnetic field of Mars is very, very weak. Why weak? See, in a case of our Earth, we have strong magnetic field because of outer core. In outer core, we have liquid ion nickel, which is constantly moving due to rotation of Earth inside a outer core, and it generates a magnetic field and electric field around the Earth. Now, these electric and magnetic field protect us from solar radiation. These heavily charged particles has ability to evaporate the entire oceans of Earth within no time. So since there is no magnetic field around the Mars, that's why there is no life, there is no water at all, and their atmosphere is very, very thin. That is 1% of the Earth. So yeah, so this figure is 3.7 billion years old. Right now, this planet looks like a red giant. Okay, now let's talk about Jovian planets. Now, these Jovian planets is further divided into gas giants and ice giants. So these Jupiter and Saturn are gas giants. Okay, these are made up of gases. And while this Uranus and Neptune is an ice giant. Okay, so what is Jovian planets? Jovian planets may first we have gas giants, and here we have predominantly helium and hydrogen. But due to presence of hydrogen and helium in such an amount, still it is not considered as a star. We know that in star we have mainly hydrogen and helium, but they are not stars. Their size is even less than that of the star. Okay, and due to this less size, there is no nuclear fusion. Okay, so they are planets only. They have lot of satellites around it. Second one, ice giants. So they contain rocks, ice, mixture of water, methane, ammonia, everything like ammonia and methane. It is in the form of ice. It is in the form of ice, solid state. So let's talk about the entire Jovian planets. So they have multiple moons. They support ring system. They have no solid surface. At least over here, here we have solid surface, and they are immense in size. Now let's see the entire solar system on a scale. So here we have our sun, 99.8%. This is Mercury, Venus, Earth, Mars, Jupiter, which is the largest planet. Venus is the hottest planet. Then largest ring in the entire solar system is in this thing, Saturn, then Uranus and Neptune, and here we have Pluto, very tiny. So now second, in Jovian planets we have second largest planet, that is Saturn. It is known for its ring, and see, the ring is very, you can say, thick. Here the length of the entire ring is you can fit Earth and Moon inside this, right? Itna distance you can see. The distance between Earth and Moon is 3,84,000, and here the distance is 2,82,000 kilometers. So it is very, you can say, lengthwise, it's very long, and the thickness is very small. It is only 1 kilometer in thickness. Lengthwise, it is. Then let's see Uranus. So it rotates on its side. One more thing, all planets revolve around the sun in a same manner, but rotation is different. Okay, rotation wise, each planet rotates west to east except Venus and Uranus. So Venus and Uranus rotates from east to west, while all planets rotates from west to east. Okay, that means suppose you are on Venus or Uranus, you will see sunrise in the west and sunset in the east. So there we have entirely different concept. One more thing, here the inclination of planet with its normal axis is very high. See, it is very high, right? In the case of Earth, the inclination is 23.5, but over here it is more than 90 degree. Okay, now moving to the next, Neptune. So it is the outermost planet, and no doubt it is the one of the coldest planet in the entire solar system. And here the temperature is minus 3.353 degree Fahrenheit. It's coolest. Everything is in the icy state, solid state. Even gases are in the solid state. Now let's talk about different belts in the solar system. So we have a asteroid belt in between Mars and Jupiter. Here we have a lot of planetesimals of different shape, different size. They are not spherical in nature. Okay, the massive one is spherical, but the small one is not spherical in nature, and they collide with each other to form meteoroids, and sometimes which enters into the Earth's atmosphere. Okay, then largest object in the entire asteroid belt is Ceres, which size is almost equal to the Texas. Then we have a Kuiper belt. Now this Pluto is a part of Kuiper belt, and the entire Kuiper belt is formed due to million of comets. Now what is comets and what is asteroid, and how they are different, how they are differentiated. So these comets are made up of dust, ice, while these asteroids are made up of planetesimals. They are made up of rocks. So this is the different. Okay, difference. And this comets belongs to the Kuiper belt, which is beyond Neptune, and this Pluto is a part of this Kuiper belt. So that's why it is not considered as a planet round. This is a dwarf planet. Some comets are even the size of Pluto. So yeah, that's why we consider this Pluto as a dwarf. Okay, see, this is the path of Pluto. Then on the outer limit, beyond Kuiper belt, we have Oort clouds. So again over here we have ice debris, and this is the age of the solar system. So if you live this Oort cloud region, you will definitely away from the this force of sun. So till Oort clouds, we have some gravitational force which is created by sun. After this, you are away from the sun gravitational force. Okay, so this entire solar system is formed around 4.57, and average wise it is 4.6 billion years ago. So this is our sun, having a fiery nature, gravitational force, having magnetic field, intense magnetic field around it. Now we'll discuss about the sun in detail as well as different planet in detail in next lectures. So this is the demo lecture and this is just a trailer. If you want to see the full picture, please come and join us. We'll discuss the entire solar system, entire universe in 30 hours lecture. That will be very interesting, believe me. So that's it for the today. Hope you like the video. Please do like, comment and subscribe and join our institute. That's it. Thank you very much.